Hello everyone, welcome to what will be pre-lecture 29. We're going to talk about Gibbs free energy here. So let me just start by defining it and why we care about Gibbs free energy, or hopefully should care. So Gibbs free energy is around because it is easier to measure than entropy a lot of the time. So we could say that all processes are basically driven by heat and entropy changes. And we actually came up with a way to relate heat and entropy in our last class. And we can relate them further using Gibbs free energy. And this is basically a way to quantify how spontaneous, or measure the spontaneity of a reaction and relate our enthalpy and our entropy. And it's actually a pretty simple equation, all things considered, for how we would do that. We can do it using this equation here, where our Gibbs free energy, which we call delta G, is going to be equal to the change in enthalpy, delta H, minus T, which is our temperature in Kelvin, times delta S, right? So relatively simple. And the reason we should care about this is the free energy is the maximum amount of usable energy or work, we would say, that a reaction can produce. And so we talked about in first semester Gen Chem how reactions can produce heat if they're exothermic, right? But heat is not always useful for doing work. So that could mean a number of things, but basically heat sometimes just literally fizzles out, whereas Gibbs free energy is energy that can be useful for performing functions, anything from like turning a turbine to literally powering your cells right now. And similar to enthalpy, which is delta H, when delta G values are negative, that is a favorable thing, meaning the process will be spontaneous under those conditions. Basically, it will always be a favorable process if our enthalpy is negative, aka exothermic, and we have a positive entropy. And so that should make sense based on what we've already talked about in class. And the word that we use to describe a spontaneous process is actually exergonic. So similar to exothermic, but in this case, exergonic. And then if delta G is positive, it is endergonic. So similar to exo and endo, but this time it's exer and ender. Okay, so those are good terms to know going forward. If we think about this in terms of just energy in a reaction, again, we have this thing called an activation energy that we're going to talk about next unit. And that separates our reactants and our products. That's why our reactants don't immediately always turn into our products, is we need some sort of barrier there. But if we compare the Gibbs free energy of our reactants to the Gibbs free energy of our products, if the reactants start higher, products end lower, that is exergonic. And then, of course, the opposite would be true for something that is endergonic, right? We have to put energy in order to basically do that. And of course, it should make hopefully logical sense that if we have an endergonic process that needs to be powered by a separate process, something in our surroundings that is exergonic. And this is basically how all of biology works. Ultimately, a lot of ATP is, when we have ATP, it's exergonic. It releases that free energy for other biological processes that are endergonic. Okay, and so I find this table to be very handy. Essentially, all we're comparing on the top here is our enthalpies, if it's endothermic or exothermic. And then on the left side here, comparing our entropy, whether we have an increase or a decrease in entropy. And this basically just tells us whether or not a process is going to be exergonic. So, for example, we already said if something is exothermic with an increase in entropy, it will always be favorable. The opposite is true then, where if we have a decrease in entropy for an endothermic process, that process is never going to be favorable. It's always endergonic. But where things get interesting are these yellow boxes here. So if we have, say, an increase in entropy, which would be favorable, but it's also an endothermic process, which is in theory unfavorable, then our spontaneous or our reaction will be spontaneous at high temperature, meaning delta G would be negative at higher temperatures, because if you look at this equation, our temperature term is tied to our entropy term. And so if we want the overall reaction to be spontaneous, we want this number to be as negative as possible to get us to be exergonic. So it would be spontaneous at high temperatures and endergonic or non-spontaneous at lower temperatures. And then, of course, the opposite's true, where if something is exothermic but has a decrease in entropy, that will be spontaneous at lower temperatures and non-spontaneous at higher temperatures. Okay? So hopefully that table is helpful for you thinking about processes and being able to identify whether or not something is spontaneous based on what we know about its enthalpy and entropy changes. We could also think about this graphically. So again, if our free energy is 0, it is the cutoff between a spontaneous and a non-spontaneous process. Then at some point, our changes in enthalpy and entropy will intersect if they have the same value, basically if both are positive or both are negative. But then we have, of course, the green and the red lines that show that no matter what our temperature is, it will always either be non-spontaneous or spontaneous. Okay? And then just want to cover 2 other quick ways that we can calculate Gibbs free energy. So this is very similar to what we talked about with standard state enthalpies and standard state entropies. These are values that you get from a table in your textbook. It's one that I will give you values for should you ever need them, where our change in Gibbs free energy is going to be equal to the sum of our standard Gibbs energies for our products minus the sum of our Gibbs free energy for our reactants. This V sign here is, of course, our stoichiometric coefficient. One of my favorites is that we can actually relate Gibbs free energy to our equilibrium constant, K, just like we did with our electrochemistry. And so when we have delta G standard, we know that that is going to be equal to negative RT and then the natural log of K, which is, again, our equilibrium constant. And then if we are under non-standard conditions, we would, of course, use Q instead of K, the reaction quotient. And then we could find delta G under non-standard conditions, but we would start with our standard conditions and then plus RT ln of Q. Okay? So those are some different ways that we can find delta G and relate it to some properties that we already know. If we think about this graphically, if you're a more visual person, then this is some way you could think about it, where if we have a graph of our free energy being on the y-axis and the extent of our reaction happening on the x-axis, if K is less than 1, we know that that reaction is not favorable as written, right? We know that from everything we've talked about this semester. And so if we were measuring pressures of a reaction and they were at 1 atm, we know that our reaction would have to shift towards the products in order to reach equilibrium, which is going to be, again, favoring our reactants instead of our products, which would be represented by, if we had an equal concentration of reactants and products, which would be represented by this middle line. Opposite will then be true when K is greater than 1. We know our reaction is going to shift towards the products, and so that means if we started with an equal amount of reactants and products, reaction is going to shift to the right. And then, of course, at equilibrium, K would be equal to 1 in the situation where we have equal concentrations. Okay? All right, that's it for the pre-lecture. Hope it was useful. If you do have any questions, please let me know. Otherwise, I will see you in class.